Can you hear me all?
Yes, sir.
Today we will be talking about searching algorithms. Okay. Now to motivate the topic, we can start from implicit and explicit searching. So what do you mean by these two terms? Implicit and explicit searching. Okay. So in implicit searching, whenever we try to find a location in the Google, so we first specify the location. Okay. And when we press the enter, then the location, uh, that location will show uh, in the Google. Okay. So thing is that if we want to find some restaurants or some hotels near some location, then what we do is specify the location. Then we can write a couple of phrase, or we can specify the name of the hotel, or if we write the restaurant with the location, then we can find some address, or we can find some locations of the hotels which will near to that specified location or specified place. Okay. So this type of searching is called explicit searching. In case of implicit searching, if we write the restaurant or hotel without specifying the name of the hotel, or without specifying the name of the restaurant, then Google will figure out the hotels and restaurant name of the hotels and name of the restaurants which is near to the user. That means the user will only write about the hotels, about the restaurants in the Google. Accordingly, Google will figure out that figure out the names of the hotel names of the restaurants near to the user. Okay. So if user is searching some hotels or restaurants by sitting in Durgapur, then or by sitting in NIT Durgapur, then in then all the names of the hotels and restaurants which are near to the NIT Durgapur will be displayed. Okay. So Google actually figure out this type of search engines, and by which the Google will display the names of the hotels and restaurants which are very near to the NIT Durgapur. Okay. So for that we don't need to specify the name of the hotel or name of the restaurant. So this type of searching is called the implicit searching. In case of implicit searching, we don't need to specify the name of the entity or name of the items that we are going to search in the web. Okay. But in case of explicit searching, we need to specify the name of the thing, or name of the locations, or name of the entity that to be searched in the web. Okay. So therefore, we can define the searching as identifying a particular record, which refers to finding a record whose value is equal to the given value. Okay. So here we try to find a record whose key value is equal to the given value. So this operation is called the searching. Now, if search result in locating the desired record, then the search is said to be successful. Otherwise, the search operation is said to be unsuccessful. Okay. So for simplicity, we can assume that each record consists of a key field only. That means this key field may be some element, maybe some character, okay, maybe some floating point number, maybe some integer. So we can assume that the record is not containing a set of information or set of key fields. So only the record will contain a key field So that may infer some number, that may infer some word, that may infer some character, that may infer some string. Okay. Now, according to the strategy of searching, we can divide the searching algorithms into two different groups. Okay, or we can say two different way we can search the entities or search the desired items in the list. Okay, one is the linear search, another is the bisection search. So in linear search, sometimes the linear search is called the brute force search. Okay, and brute force search is sometimes called the British Museum search algorithms. So in linear search, what we do, we search the element by enumerating all the elements from 1 to n. Okay, so the idea of the brute force search is to first we enumerate the numbers from 1 to n. Here n is the total number of elements or total number of items or total number of records in the list. So first we enumerate the items from 1 to n, and then we initiate the search operation. So in this search operation, list is given unsorted. Okay. So in linear search, list is given unsorted. Okay. But in case of bisection search, list must be sorted to give the correct answer. So as part of the bisection search, as part of the bisection search, we can have the binary search algorithm. In binary search algorithm, the list is given as sorted. Okay. So, but in case of linear search, a list is given unsorted. Now, what is linear search? How the linear search is performed? A simple way to search for a key value k in an array A is to compare the values of the elements in A with k. Okay, so here A is an array and k is the searching element. That means this key value k will be search in the list A. So for that we need to compare all the values of all the values of the elements in A with k. Okay. Now we can initiate the search process with a comparison between the first element and the searching element k. Okay. So in this comparison, we can compare the first element of the array A with the searching element k. Okay. So if we find that this search does not give any result, then we can proceed for the next element of A. That means then the second element of A will be compared with the searching element or the searching key value k. Okay, and the process will terminate when the list is exhausted or a comparison result in a success. Okay, so this method is searching is known as the sequential search or linear search. Now we will see that if in both the cases, like when the list is given unsorted or when the list is given sorted, in both the conditions we can perform the sequential search. So idea of the sequential search or linear search on a unsorted list A is that we need to first we enumerate the list from 1 to n. That means enumerate means we need to check the validity of each of the elements. Okay, so validity means here we compare. So here the main operation is the comparison operation. So here we will compare the given key value k with each of the elements in the A. Okay, so each of the elements of the array. So if we start comparing the elements from left hand side, then the first element will be picked up. Okay, then first element will be compared with the given key value k. If the search is unsuccessful, that means if the given key value is not matched with the first element of the array, then we can proceed for the next element or the second element. Then the second element again will be second element will be compared with the second element will be compared with the given key value k. Okay, and we will continue until and unless we get the match for the searching element k or the key value k. Okay, so in this search algorithm, first we need to initialize an index I equals to 0. Okay, now as long as I less than found to be end, we will try to match the given key value k with each element in array A. Okay, so here here we keep the checking for getting the match between given key value k and the and ith element. Okay, so if the match is found, then we can break the while loop. Otherwise, we will go for the next element, and that is why the here I is incremented by 1. So here we have written I plus plus. So this denotes that when the match is not found for the earlier elements, then we can go for the next element. Then the next element will be compared with the given key value k. Okay, now when when I less than is found to be n, then we can return I. So this I is the searching element which has been found to be matched with the given key value k. Okay, so this I will return, this I will indicates the position of the searching element. Okay, which has been found in the array A. Otherwise it will return -1. That means for the unsuccessful search it will return -1. Now, when we first compare the given key value k with the first element of the array, then if the first element is found to be the searching element, then number of comparison will be 1. If the second element is the searching element, then the number of comparison will be 2. Okay, so for if we get the searching element at the end of the list, that means the if the last position the searching element is found, then the number of comparison becomes n. Okay, for n number of elements. So therefore here the position is important. So if we so for ith element we will have the ith number of comparisons. Okay, so in the best case, so the best case time complexity will be order of 1. That means the constant time complexity. Okay, and for if we get the searching element at the last position of the list, then the number of comparison becomes n. So therefore in that case the worst case time complexity will be order of n. Okay, now the algorithm is based on the assumption that A contains distinct elements. So if we assume that A contains distinct values, then we can figure out the number of comparisons to be required for either successful or unsuccessful search. Okay, for unsuccessful search, the number of comparison is not fixed. Okay, so but if we consider the elements are not distinct in the list A, then the searching element will be found. Then the searching element will be found same for n number of positions. Okay, that means in all positions the same searching element will be found if the search is successful. If the search is not successful, then despite having the same values, the searching becomes unsuccessful. Okay, so therefore the number of comparison is not fixed for the unsuccessful search. It depends on the position which k occupies within the array. Okay, now if it is the first element, then only one comparison will be required. If it is the last element, then n number of comparisons will be required, and I comparisons will be required to search the ith element. Okay, now we are considering that p is the probability that the ith element will be searched. Then the expected number of comparisons for successful search is given by this expression. So here P0 is the probability for searching the first element, P1 is the probability for searching the second element, and Pn minus 1 will be the probability to search the last element. So if we sum up all this sum of product between the number of between the probability, okay, and the position, then we can have the summation over I into pi. Okay, so here I is the ith element and pi is the probability of the ith element. Okay, so here we get the summation over I into pi from I equals to 0 to n minus 1. Yes, yes is the total number of comparison. So this is the expected number of comparison for a successful search. Okay, where the element values are distinct in the list A. Now we can assume that any element is an equally likely candidate for searching. Then we can have P0 equals to P1 equals to Pn minus 1, and this gives us 1 by n, because if the each element in the list A is an equally likely candidate, then we can have the probability for each element becomes 1 by n. Okay, so in this case we can have the expected number of comparisons Cs becomes 1 by n into summation over I, where I varies from 1 to n. Okay, so if we make this summation to be evaluated, then we get n into n plus 1 divided by 2 for the summation over I, and 1 by n is already there for the probability of each element. Okay, so when we multiply 1 by n with n into n plus 1 divided by 2, we get this n plus 1 divided by 2. Okay, so this is the n plus 1 divided by 2 is the expected number of comparison for a successful search, when the probability will be found to be same for all the elements. Okay, now in case of unsuccessful search, all elements must be examined unconditionally. Okay, so therefore the expected number of comparisons in case of unsuccessful search becomes n. Okay, so yes is the expected number of comparisons in case of unsuccessful search. Yes equals to n. So that means after having n number of comparisons, if the search is found to be unsuccessful, then the expected number of comparison for unsuccessful search becomes Cs equals to n. Okay, so n means the here total number of elements becomes the expected number of comparison for unsuccessful search. Okay. So here the time complexity for successful search, if we consider the best case, then the best case time complexity becomes order of 1. That means the constant time complexity. Okay, that means if the searching element or the key value, given key value, is found at the first position. Okay, that means when we start comparing the first element with the given key value k, if the first element is found to be the searching element, then only we can have the best case time complexity, which is order of 1. Otherwise the worst case time complexity will be order of n for getting the searching element at the last position. Okay, and for time complexity for unsuccessful search will be order of n also. Okay, now the same linear search will be performed on a sorted array. So in the first algorithm, we have seen that linear search algorithm is performed on unsorted array. Now the same linear search algorithm will be performed on sorted array. So in that case, we need to in that case we need to compare the we need to compare the initialized value of u with n. That means here we compare. That means the comparison, the comparison operation will be same. That means we compare the given key value with each of the elements in the sorted array. Okay, so here the list is sorted, and the comparison will start from at the beginning, or from the left side of the array, and then one by one the element will be compared with the given key value k. Okay, so that is why we have initialized we have initialized u by 0. Okay, and here u is compared with n. So as long as u is found to be less than n, then we can go for comparing the given key value with the first element at zeroth position, and if the match is found, then we can assign the u. The u here, u is the index position of the element. So here index will be assigned to j, and then we break the while loop. Okay. Otherwise, what we will do, we will compare the element at zeroth position with k again. That means if the element is found to be greater than k, then we will break the loop. Otherwise, we will go for the next element. So for go for the next element, we need to increment the index position, or we need to increment the index of the u. So here we are incrementing u by 1. Okay, so this to be done when we will see that element at the specified position is found to be less than k, then only we will go for the increment of the index u. Okay, and here return j is used to return the position of the searching element that is to be found after matching the given key value with the intended element in the array. Now for the sorted list, when we perform the linear search algorithm on sorted list, for that we need to evaluate the time complexity. Okay, so there is no change in the expected number of comparison for a successful search. The number of comparisons required for an unsuccessful search depend on the given value of k. Okay, so here k will define here the given value k will define the number of comparisons which are required for an unsuccessful search. Okay, here the number of comparison for unsuccessful search may be 1 in the best case. Okay, that means if we have a list, if we have a sorted list which start from 10, and the given key value is found to be 5, then since the 5 is less than 10, therefore we cannot search the element. Okay, and for that the number of comparison for unsuccessful search may be 1. So after getting compared with the first element, we can decide whether the searching element will be found in the list or not. Okay, so the number of comparison for an unsuccessful search may be 1 in the best case, or n plus 1 in the worst case. Okay, so this value may lie in one of the n plus 1 intervals which are created by n elements. So here the n elements basically creates the n plus 1 intervals. Okay, and if k lies in any one of these intervals with equal probability, then the expected number of comparisons will be given by this expression cs equals to n into n plus 3 divided by 2 into n plus 1. So we get this uh, number of comparisons by adding the noun comparisons for each element in the array. Okay, so for the first element, we have to compare. The number of comparison will be 1. For the second element, number of comparison will be 2. For n elements, the number of comparison will be n. Okay, and since there are n plus 1 intervals, therefore we can write that 1 plus 2 plus n plus n divided by n plus 1. Okay, so here we get the expected number of comparisons, which will be divided by n plus 1, because here n plus 1 is the number of intervals, and this will give us n into n plus 3 divided by 2 into n plus 1. So this is the expected number of comparisons with equal probability. So in this case, the time complexity becomes order of n square. Okay, so here n will be multiplied with n square n. Okay, so therefore we will get n square plus 3n divided by 2n plus 2. Okay, so here the dominant term is the n square. Therefore, based on the dominant term, the time complexity will be decided. So therefore, the time complexity becomes order of n square. Okay. Now we will be talking about binary search. So binary search is a part of bisection strategy. So here the binary search is performed on a sorted list. So it first makes a comparison between searching element k and the middle element of the list. So what we do, we repeatedly divide the given sorted list into two equal halves. That means every time when we get this division into two equal halves, then one half, either the left or the right half, will be eliminated. So whenever we will be getting the confirmation about the searching element, whether the searching element will be found in the left half or the right half, according to the comparison with the middle element, we can decide about the elimination of the one half. Either we can eliminate the left half or the right half. So we perform this division repeatedly on the given list. Okay, so if we first go for the division of the initial list, then we can have the two halves first, based on the middle element of the list. Okay, and whenever we compare the given key value with the middle element, and based on the comparison, we will eliminate either the left half or the right half. Okay, then the remaining half, again we will initiate the division on the remaining half. Okay, or the remaining list. Okay, and then we will get the middle element. Again we compare the searching element, or the key given key value with the middle element. Then based on the comparison, we can decide about the searching element to be found either in the left half or the right half. Okay, so this comparison will result either in the match between k and the middle element of a, or we can identify the left half or the right half of the array, which which decide the desired element to be found. Okay, or desired element may belong. So here each comparison enables one eliminate half of the elements from further consideration, and because of this method is called dichotomous search. So binary search is also called the dichotomous search, or it is also called the bisection search. As it is a part of the bisection strategy, therefore it is also called the bisection search. It is also called dichotomous search, because we are eliminating half of the elements after each comparison. That is why this binary search is called the dichotomous search. Now let us try to understand the binary search from this example. Okay, so here we have a list of 7 elements, Okay, 3, 4, 5, 6, 8, 9, 11, and here the searching element is 8. That means here 8 will be searched in the given list. So in the given list we have 7 elements. Okay, so when we have odd number of elements in the list, there will be only one middle element. If we have even number of elements in the list, then we have two elements to be the middle element. But since we cannot consider the two elements simultaneously as middle element, therefore any of these two elements becomes the middle element of the array or the given list. Okay, so here we can see that we have odd number of elements in the given list. So here we will have only one middle element, that is 6. So first we compare the given key value 8 with 6, where we can see that 8 is found to be greater than 6. Therefore, we can eliminate the left half of the middle element 6. Okay, so after eliminating the left half including the middle element, then we will go for the right half, and right half will contain three elements only. So 8, 9, 11. Then in among the 8, 9, 11, 9 will become the middle element. Okay, now the given key value 8 will be compared with the middle element 9. Okay, so here we can see that 8 is found to be less than 9. So therefore we will go for the left half. So left half will contain one element, that is 8. Okay, and right half will contain 11. So here the right half will be eliminated including the middle element 9, and only one element to be remain in the list in the left half, and that is 8. So here 8 is when the 8 is compared with the given key value 8, then it is found to be matched. That means the given key value is match with this element. Okay, so therefore here we found the match between the given key value and the element of the remaining list. Okay, so that means after how many times we compare? We compare here three times. Okay, that means after three comparisons we get the desired result, or we get the desired output. So here number of comparison means the number of iterations. So after three iterations we get the match in the list. Okay, so this is the function definition for binary search algorithm. Here we have defined the binary search algorithm. So in this binary search algorithm, if we consider this list, then the left end of the list will be considered as lower, and right end of the list will be considered as upper. Okay, so here we have defined two variable. One is the lower, which is initialized by 0. Okay, and another variable is upper, which is initialized by n minus 1. And we are taking another variable, that is mid, and this mid will denote the middle element of the list. And another index here I is taken, which is initialized by -1. Now in the while loop, as long as we found upper greater than equals to lower, then only we get the middle element. That means the middle element will be determined by getting the sum of upper and lower divided by 2. Okay, so this will give us the middle element. Then after getting the middle element, we will go for the comparison with the given key value k. Okay, so here we have kept a checking where we checked whether the given key value k is found to be equal to the middle element or not. If the match is found, then we will assign the index of the middle element to I, because initially I was assigned by -1 or initialized by -1. So whenever the middle element will be found to be the match to the given key value k, then we will assign the middle, we will assign the index of the middle element to I. Then we break the loop. So otherwise, what we will do, we will check whether k is found to be greater than the middle element or not. If the if k is found to be greater than middle element, then we go for then we will define the lower then we define the lower index of the list, that is that becomes mid plus 1. Okay. Otherwise, we will define the upper limit or the upper bound of the list, that becomes mid minus 1. Okay. So whenever k is found to be greater than the middle element, that means we will go for the right half. Otherwise, we will go for the left half. And when we will go for the right half, the lower bound becomes the mid plus 1. That means before the middle element, we will eliminate all the elements of the left half. That is why we define lower bound as mid plus 1. Okay. And when k is found to be less than the middle element, then we will go for the upper bound, which is to be defined as mid minus 1. Okay. And finally we return the index position of the searching element that has been found in the list. Now, to analyze the performance of the binary search, we will consider the maximum number of comparisons to be required for a successful search. Okay, so that to be computed first. So for that, we can assume that after k iterations, the binary search terminates. So at each iteration, the list is divided by half. So we assume the length of the list at any iteration is n. Okay. So for the first iteration, the length of the array becomes n. For second iteration, the length of the array becomes n by 2. That means in the second iteration, we divide the array into two equal halves. Okay, n by 2. And in the third iteration, the length of the array becomes n by 2 divided by n by 2. That means n by 2 to the power 2. Okay. And after kth iteration, the length of the array becomes 1. That means we are assuming that after kth iteration, the binary search terminates. So at kth iteration, the length of the array becomes 1, because we are dividing the array every time, or every iteration we are dividing the array into two equal halves. And after comparing with the middle element, one half is eliminated and another half is remain for the next iteration. In the next iteration, the remaining half is again divided into two
Sir,
equal
we have
halves.
a class.
So in this way, after kth iteration, we will get the length of the array to be 1. Okay, that means the after kth iteration, the length of the array becomes 1. So therefore, we can say that the length of the array to be n by 2 to the power k, because after kth iteration, n by 2 to the power k becomes 1. Okay, that is why we are writing n by 2 to the power k equals to 1. Okay, and this implies n equals to 2 to the power k. Now if we take the log on both sides, then we can have k equals to log n base 2. Therefore the time complexity order of log n. So that means the time complexity will be logarithmic time complexity. When we get the logarithmic time complexity, when we divide the problem size into small number of problems. Okay, that means the size of the problems will be divided into small sizes. So in that case, we will have the time complexity in logarithmic time complexity. So similarly here, since we are dividing the given list into two equal halves. So this division is done repeatedly on the remaining list. So therefore, the time complexity becomes the logarithmic time complexity, which is order of log n.
Sir, sir, we had a class from 2:15.
Any questions from here? If you have any questions, you can ask me. Otherwise, we will stop now. And in the next class, we will start the sorting algorithms. Okay, that's all for today.
Thank you, sir.